Yeah, oh. All right, hi, my name is Madeline Roark, and I'm a summer intern on the automation team. And here's a little bit about myself. So I'm from Georgetown, Kentucky, but I'm actually adopted from China. I'll be at the University of Kentucky as a junior this year, and my major is mechanical engineering with a minor in computer science. Some of my engineering background, so I know quite a bit about programming in C++. I got most of my mechanical experience from Roark Machining and Fabrication, which is this family-owned business we have. There I learned how to use the industrial saw, and I learned a lot more about fabrication. I also went on a bunch of Toyota installations there, so I got familiar with the shop floors. My middle ground experience, I learned how to set up and use the water jet, the manual mills, the Haas mills. Then I also learned a lot about Autodesk Inventor, finite element analysis testing, center gravity testing, and then I also learned how to project manage. So my project was assigned at Plasman in Lawrenceburg, Tennessee. There they make mass transit window frames like for buses. This process that's shown in the picture is actually one of the bus frame windows. It's just one of 7 different types of frames they have. They have 7 different shapes and sizes they make. Whenever I visited, I saw that the team member was taking 200 steps per frame, averaging 6 minutes, while they make 35 frames per shift. There's 2 shifts, there's a day shift and a night shift. What we really want to see out of these ideal conditions is to decrease the travel. So we want to get the footsteps down. There's 10 solid steps that get this frame to be able to be racked up and ready to go. And a lot of those steps include traveling around a lot, circling the table. Those are where your steps comes from. Then we want to eliminate the ergonomic strain. So right now the table sits around 30 inches. So that's just a little bit below waist level. And the biggest ergonomic strains in this process we see is in number 4 and number 10, where we're having to physically pick up the frame. It's pretty wide, and I actually got to run this process. I learned how to do it. I made a couple frames. The biggest part was picking it up myself. As 5'2", I needed help on that, and it was very strong on my back. So those are big safety risks for the team member. Then we want to organize the tools and supplies. As you can see on the top, there's a bunch of clutter. On the bottom, there's clutter. Team member mentioned to me how we're spilling urethane on the frames, we're spilling primer on the frames. So those are steps 7 and 8, and we're having to trash those frames. So that's another big quality aspect in this process. And we want to accommodate for all 7 frames on the tabletop. So those will be our ideal conditions would all increase the productivity of this process. So as far as our DMM decision-making matrix, we could keep it the same. Safety aspect would obviously X that out. Number 2, we can make it an automated robot, or number 3, sorry. Number 3, we can make it a fully automated robot. The ROI would not be good in return for this option. So the ultimate idea was to redesign the table. And as you can see, the table right now can't really be modified to fit our ideal conditions. So our ultimate goal is to just redesign a new table. So this is my design and what I drew up. The first picture on the very left is the table sitting at rest, and then when you apply pressure to one end, the frame can actually come to you, and then we can also swivel it, and there's the tabletop view. So some of the improvements I've made is I added a height adjustment. So I found that the standard height for tables, working tables, is usually around 40 inches. So then I decided to add some hydraulic legs that have electronic buttons, so that can take the 40-inch table and it can go up to 7 inches, depending on comfortability and where you want that at. Next is the tilt part. So the tilt removes most of the ergonomic strain as the frame can come to you. Everything in green right there is what makes the tilt happen. The rotor discs, the pillow block bearings, shaft collars, shaft. The way you can lock this in place is there's double acting pneumatic caliper brakes on both discs. So with a foot pedal, you can press the foot pedal in, engage the whole frame so it can move freely wherever you want it, and then just lift off to lock it in place. Next is the revolving tabletop. This part gets our footsteps down. So that's the part in red on top. That's our slew bearing, and it has a pneumatic cylinder to stop the rotation. Again, with the foot pedal, just press it in, move it, and then release it and it locks. Then we have the fittings. So those are the blue parts on the frame. Those accommodate for all 7 frames, and they also prevent the aluminum damage from getting on the frames. Then our center of gravity weights. So the center of gravity weights basically is a safety precaution for the table because it wouldn't function right if we didn't have those. Say I was putting pressure down on one side and I didn't have those counterweights, our center of gravity would be above the pivot point, causing the table to eventually flip back up and hit me. So that was a big safety concern for this design. With having that, the counterweights have 100 pounds on each side. So with that, we're questioned, what does this do to the material that's holding 200 pounds on it? So I did a finite element analysis test, and what this does is it assigns material and weight to each of these components in this project, and it can tell you where the stress points are. So the stress points are moderate. They're not enough to damage it permanently or deform it. So I did want to counteract that just in case. So I added and designed 2 gussets and I put them on each side. And as you can see, it doesn't really get rid of all the stress, but it does relocate them from a wider area to a smaller area. So this prevents any deformation and it eliminates any risk of tensile damage. So that's like ripping or breaking of the metal. Then I'll go into my bill of materials and my return on investment. So everything ended up being around a little under $22,000. We sent in a CapEx request, $30,000, but we added some room for taxes, shipping, and the rest we'll just send back to plasman. So after the installation, 1 team member will perform the assembly. We anticipate a 30,000 throughput and a potential 1 headcount reduction. We do take out a headcount, so that would be the night shift. We would be saving 85,000 throughput. And our equity value creation would go up to 644,000, with a return on investment years with labor at 0.7. But if we kept it at 2 headcount, which is what we anticipate, we'll still save 30,000 a year, and our return in years with labor would be 2. So this is the timeline for the project. The money actually just got in today, so it'll be 8 weeks from today, and then the project will be installed. Some lessons that I learned. One gap that I've noticed with learning CAD in school compared to learning stuff in the real automotive world is that you can't always build complex designs. I've learned this because of fabricating and working closely with fabricators, and a lot of times being told I can't make this. So then the next thing is, to me, as a mechanical engineer who doesn't know a lot about business or private equity, I realized that an automation team is a privilege to have, and that not all private equities have automation teams. So that was cool to learn about. And then the next thing, room for improvement. I would have liked to see this project go through, but since the funding was on a weird timeline, I couldn't get to see that. I would like to come back when it's completely finished and just look at it and just see it completed. And then communicating with the portfolios, the current conditions of the projects for the plant visits and the project assignments. So one thing I noticed is that when I was looking at the video of the team members working on this project, I think it was taken a year before we went in, but there were 2 team members working on it. But when we got there, it was really just 1. So that kind of messed up with my expectations and my numbers. So I want to also thank all the engineers that helped me with this project. Any questions? Yeah.
Did you say you went to look at this process and
Yeah.
had the portfolio covered?
Yes.
Did you talk to the people that run the process?
Oh,
and kind of
yes.
Get their feelings, and what did you learn from that? Activity?
Yeah, he was the one, I talked to this team member named Wesley. He was really nice. I learned he's super into metal rock, but he was the one that told me, the supplies in the middle is getting out of control. Like he was spilling the primer and the sealant, and then I also asked him on some advice on like some changes that I was thinking about making, and he just kind of reassured me that that would be a good idea to have a height adjustment and stuff like that. So,
You mentioned the engineers that you worked with, like of that design, was that like all you? Like, I'm just curious, like what, looks pretty intense.
yeah, so I drew all of it by myself on Autodesk Inventor. I obviously didn't know what a lot of these like mechanical functions were, so I got help picking out, like I needed a pneumatic brake with spring in it to work with the valves on the pedal. I had no idea what that was, but as far as the design aspect, yes, I drew all that up.
Right?
Very good.
No.